Warm welcome back to the afternoon session here, and it's my pleasure and privilege to welcome Philip Dutkoski, one of the true giants in machine perfusion. Philip is like me from Germany, has migrated in different direction to Switzerland, where he has been working in Zurich for a long time and has recently moved to Basel. And so Philip, we would love to hear from you your views on assessment of liver graft quality during HOPE. And we would really want to learn from you and your vast experience. So a warm welcome to Leeds, although you're remotely. I had so much hope to meet you here. So all the best.
So many thanks. I'm very happy to say something about HOPE. I think there was already much information about that, and very sorry that I couldn't come to Leeds, but I will try to make at least understandable talk. So the topic is difficult. You are, of course, introduced to ask any question. You can also interrupt me. So I try to be easy. It's about assessment of liver graft quality during HOPE, and always if I say something about that, it's for me a miracle that we speak 60 years after introduction of liver transplant. This is already 60 years ago, and that we speak only now about assessment of liver quality before we actually use them. So the idea, of course, of hypothermic and oxygenation is an old one. You know that. For the kidneys, for example, it has been introduced by Volkert Belzer, and also for livers by Tom Starzel already in the 1970s. But at the moment, we understand that HOPE is something which is not continuously. It may be better to do it up front, but at the moment, the definition is, if I may say so, an endoischemic, relatively short approach. So we speak about a kind of conditioning. This is a kind of liver conditioning, like you upload your cell phone. So 2 hours or 3 hours. It's a short procedure. It is at the moment not very frequently used to bridge transplant, although you can do that, but it is not a topic at the moment. So it's introduced after cold ischemia and for a short time and at a low flow. So this is what we understand at the moment for HOPE, and it started a group of people started to do that in rodents in more than 20 years ago, and so that was a purely experimental stuff. At the same time, Peter Friend did his groundbreaking experiments in Oxford, but usually when we met at meetings, we were speaking in front of empty rows, and there was not much interest, I have to say, in the world for machine perfusion. So we constructed many machines for different kind of species, rodents and pigs, and at the end, of course, also for humans. But it started only 10 years ago, that I would say, at least for my knowledge, the first DCD liver was perfused in 2nd January 2012, and it's not long ago. And at that time, you see, there were only 6 or 8 livers perfused worldwide with this kind of technique, and so that is a very small number. And therefore, it's surprising that we have now an experience suddenly of 6 RCTs in the last 3 years. So it's a kind of explosion. The same also for the normothermic or NRP story. So there's a lot of interest, and I think we speak now about a long-term knowledge which we need to gather. And it's not only that we speak about HOPE. You know that we speak about in the world about different perfusion techniques and different kind of machines. It's a kind of machine perfusion hype. But what is frequently, what I at least frequently hear, and at the congresses are these things. So many people stand on the stage, including me, and say, I have the highest injured liver grafts. I can rescue nationwide discarded livers. I have, of course, the best utilization and the best outcome. And so therefore my perfusion technique is superior. And I think we have to say that this is not true, because we have highly variable risk definitions. We have obviously large differences between countries in terms of waiting times and also the risk, and the utilization is most often not referred to the offers, it's referred to the livers retrieved, which is a difference, because the first offer is very frequently rejected without retrieval, and the best outcome is most often referred to first week lab data, and there's no comparison of machine perfusion techniques in RCTs except of one, which is at the moment recruiting in Germany, but is far from being complete. So therefore, I have to say the randomized clinical trials, and you heard that before, the machine perfusions reduce acute liver injury, they reduce post-reperfusion injury, they increase also the duration of preservation, probably both procedures, cold and warm, but surprisingly, we have not much heard about organ viability assessment, at least in the randomized trials, and increased organ utilization is very difficult to address as a secondary endpoint. And therefore, I think it is time to speak about mechanism, because if we want to understand, for example, what can we measure during cold perfusion, in addition also to normothermic perfusion, we need to understand what is happening. And it's happening a lot, because we know that on Earth, at least, the human species has to breathe. We need oxygen, and so the lack of oxygen is our central problem. So if there's no oxygen, the tissue is not in good condition. And that's an old statement by Jim Southard, who I met, by the way, in Wisconsin. So ischemia in organ transplant is everywhere. And the problem is, it is at different steps. So we have at least 5 steps where hypoxia or under-oxygenation of tissues is present. And that starts in the donor with a cerebral event or the cardiac event, depending on your graft type. And it follows in the reanimation phase, because, of course, we want to rescue many people which suffer on terrible accidents or diseases, and afterwards there is brain death, and there's also a kind of hypoxia or DCD, which is involved, of course, with correlated with ischemia. And we have procurement, where, of course, also under oxygenation is most often the case, and afterwards we need time to implant livers or kidneys or lungs, and that is also a phase. There's also a phase which we cannot ignore, that we have here a problem with the oxygenation. So even if we put livers on, regardless of the machine type, we have to say all these machines, they come at the end of different hypoxia phases. And I would say the conclusion of this is that all ex situ perfusion strategies come too late, except if we choose an ischemia-free perfusion approach. And this is the first statement which I want to make, and therefore we have to struggle with the events which happen during ischemia. And there are 2 events which are well known since more than 10 years, and this is an accumulation of metabolites before they are oxidized. So if there's a lack of oxygen, they cannot be metabolized, so they accumulate, and this is in every species. This is in rodents, in pigs, in humans, and you see it is more in the red line than in the blue line. The red line is warm ischemia, the blue line is cold ischemia, but they accumulate anyway, and at the same time energy is broken down, which is logical, because the mitochondria cannot metabolize the substances without oxygen. So we have 2 things. We have an accumulation of metabolites and a depletion of ATP, and that is happening in every in every organ donation, even in DBD, and in every species. And in all organs, you see the columns is the red one is the metabolite which is increased. This is succinate, and this is more in livers, unfortunately, than in the other organs by the factor of 5. You see that the axis is different here. That's 25, and this is 5. So there's a difference between the organs, but basically the message is there's an accumulation of this metabolite, succinate, and also by other purine metabolites in every species and in every organ. And this is a problem for mitochondria because if for example, there's a reoxygenation like in the implantation phase or also on the machines, then obviously there will be a problem at the first electron complex because there's a sudden increase of electrons by introduction of oxygen, and that leads to a huge oxidative stress at the first protein complex in mitochondria, and that is happening also in every organ. So we need to understand that this is something which we can probably not avoid. And so that is a picture which I made just to illustrate that if you have two basins of water and the water falls down a certain gradient, so and there's a wheel here. The wheel is of course driven by the waterfall, so that makes the energy because the water is falling down. And if you, for example, stop the water flow by a certain gate, there is no turning around of the wheel, but at the same time there's a slow increase of water or electrons, which are the surrogate of this picture. So, and the most known surrogates of this is, and the most known electron donors are NADH and succinate. So they accumulate if the gate is closed, and the water cannot go down and the wheel is not turning, but they accumulate. And if you suddenly remove this gate, there is a sudden increase of waterfall or electrons, and the message is the wheel gets broken. And so this is a problem for mitochondria. A sudden overflow is the problem. And if we want to address that, for example, in machines or in before we implant organs, then we need to avoid this sudden overflow because it has huge consequences, because it is triggering a lot of dangerous signaling and is activating all receptors in the cells and causing a so-called sterile inflammation. And then it's too late, of course, to avoid that. But there are some logical things which we can do. For example, the most logical would be to prevent accumulation of electron donors like succinate or NADH. And we cannot. The point is, because I said that, we come too late with all our machines. Even if we put something in the perfusate, we can obviously not avoid that, because we are not a smart, I would say, animal on the planet. Like, for example, the Siberian wood frog, because he can dive because he doesn't want to freeze in the cold water in Siberia. He wants to dive in the water because that is not freezing. But unfortunately, he has no oxygen underwater, so he's diving and not freezing, but hypoxic. He's for 2 months underwater. And if he comes to the surface, he has no reperfusion injury because he managed to avoid accumulation of succinate by the factor 40. So there are species on Earth which can avoid succinate accumulation and can get no reperfusion injury. And we need to learn that. But at the moment, we cannot change that. Maybe we can change that in the donor later in the future. I don't know that. But at the moment, we cannot. So the key probably is to prevent a rapid electron donor accumulation during reperfusion, a so-called slow succinate oxidation. And the only key which we have is, in fact, hypothermia, because hypothermia is reducing all these processes by the factor 10 or 8, and therefore reperfusion goes slower. And in addition, we have a trick. We can do that on machines, because if we, for example, reperfuse on machines, then of course we have a kind of reperfusion light. So advantage of any ex situ reperfusion on machines would be that we have less cause mito injury, for example, by decreasing the temperature. And we can use asanguinous perfusates and use the absence of leukocytes, and we can do that ex situ on machines and avoid systemic danger signaling. And therefore, I think machines are interesting because regardless of their technique, they cause less reperfusion injury as seen in the human. And at the same time, we can also play a little bit with the mitochondria. We can actually, for example, if we do HOPE at a relatively low temperature, 10 degrees, then we can improve the complexes by in the first 2 hours. So that was shown. Complex 1, 2, and 4 are improving during HOPE, and at the same time we can metabolize the accumulated succinate and increase the ATP, like charging the battery. And then, of course, the organs go metabolically treated in the implantation phase. And this is a huge effect, which is not only targeting ATP, but all these metabolites which are marked with an arrow. So they are all changing within a few hours. So it's a huge metabolic effect. But now the topic is that we speak about assessment, and therefore we are interested to monitor this treatment effect, which we obviously trigger during HOPE perfusion. And it makes sense that if mitochondria are the initial ubiquitous problem in every organ and in every species, why not measure their function? And therefore we come to the idea to measure what we are doing during HOPE. But this is difficult because, of course, we could take PCR analysis or mass spectrometry or proteomics, or we take biopsies, but all this will take a long time. So can we do something very smart, which is easy during this HOPE perfusion? And therefore we looked more closer to the electron transport chain and we'll try to understand what happened here. And therefore I have to quickly say that to use normally the flow of the electrons, which is this is also happening during HOPE. So the electrons are transferred from complex 1 to complex 5 to make at the end ATP. So this is the direction, the so-called forward flow. And in the complex 1, these electrons are transferred from something which is called FMN. This is a flavin protein, and then they are transferred to iron clusters, and at the end to ubiquinone. So that's a chain, a difficult chain, and at the same time protons are pumped from inside to outside, and so that's the function of the first electron complex. And the point is, if the gate is opening after ischemia, as I said at the beginning, and this overflow happens because the electrons are going in the wrong direction. It's a called of reverse electron transfer, so they go not in this direction, they go in the back direction for reasons which are not fully understood. Even mitochondrial cracks cannot fully explain that, but obviously they go in this direction and induce at this molecule, the prosthetic group, at the docking side of NADH. They use a problem here because that molecule is released, and this is the flavin mononucleotide. And at the same time, if this is released, because it's a prosthetic group, the complex 1 is severely injured. And if it is injured, it cannot obviously transport electrons in the normal way. So if the message is if FMN is released, there is less function of mitochondria, and at the end less ATP and increased hypoxanthine. So the FMN release is a surrogate marker for complex 1 injury and mitochondrial function. And this is interesting for us. So, because if there's a lot of FMN release, there's obviously less or low ATP and vice versa. And this FMN story is in reality very difficult, because you see it's a very small molecule sitting in the middle here, covered by different chains. There are long chains and small chains, and this is actually different in several organs. So, for example, in brain, there's a short chain, and FMN is better kept at his place, and therefore there's less reactive oxygen species during reperfusion. And this is the opposite in heart. So there's a different kind of chain which is keeping the FMN at its right place, and so this causes a much higher increase of reactive oxygen species. So the message is here that there's a different type of FMN release in different organs, but it happens in every organ, but to a different amount. And the good thing for us is this happens during reperfusion with a less or more degree, and we can relatively easily measure that because it's a natural fluorescent stuff. So if the message is if you send light on this molecule, it comes in a different wavelength back, and therefore you can measure that, like in NADH in all these ELISAs which are available. So you can measure that if for example, the perfosate is without much other substances, like it is in acellular perfosate. So the acellular perfosate is, of course, advantageous to measure FMN. You can also measure that in sanguineous perfosates, but you have to centrifugate first that, and therefore you cannot measure that online. But if it is a acellular perfusion, then it is possible to measure that in online fashion. Just by measuring the fluorescence. And we did that, you know that probably, so you basically in the last 6 years we put basically every DCD, also some DBDs on HOPE perfusion, and determined this FMN, and at the end we took all these livers and paid the price and see what happens if the FMN was very high. We had some PNF and some NAS, which we don't want to see, and therefore we created a kind of traffic light. So green would mean there's zero consequence, orange would mean that we have some, but to a small amount, some problems, and red would be we don't take it, because the difficulty was in the last 4 years to set up a threshold when to use or not to use livers or kidneys or lungs. And this is interesting because we can measure that, as I said, for example, with the VitaSmart pump instead of going to a microplate. So microplate is of course feasible. The measurement in the microplate is 10 minutes or something like that, but you have to pump 30 minutes, then measurement. So it's an amount of 1 hour which it takes to have the analysis, and real-time analysis would be, of course, more precise for us and quicker at the end, because then you can also consider the slope of this curve and not the whole the cumulative value. So this is an example of an online measurement with a sensor put on the tube, and you see there's a relatively steep increase of FMN. This is the microplate result, and it's correlating, but you see that online, and you have this information of the slope even in the first 10 minutes, you know that this is getting very high. So it's a quicker information. For example, if we compare that to this graph, so we don't take this graph and we take this graph, and of course you can ask, does it make sense if we do this? Do we not waste livers? And therefore we did an international validation of this. So this is the result of 10 centers in 7 countries, and we speak here about 473 liver perfosate samples, and we measured the values in our center. So all these perfosates were collected and sent to Zurich and were measured there. So they were not measured by the centers. This is a disadvantage, but is the first study of this kind. So it was a central measurement, and you see the variation is a variation between centers, but basically the information is that most of these values were different if you compare that to the discarded ones, and that is the fluorescence measurement, and that is the validation with the mass spectrometry, because the argument was always, do we measure the right thing? Is that really the molecule which we want to see? But I think it is the molecule, because we did several attempts to identify the type of FMN. And so I think we are pretty sure that this is a good correlation of mass spectrometry and fluorescence, and we can even calibrate that in by the microplates, for example, or also by the real-time measurement. So we know exactly the amount of FMN in micromole per milliliter. And if we now want to see, is there a prediction? Is that useful to measure that? You see the ROC curve for fluorescence is 0.77, the C statistic, in terms of graft loss, regardless of PNF or cholangiopathy in the first year. So it's a pretty good correlation, and even better if we look at the mass spectrometry. So here the ROC curve was better, 0.84. So I think that's quite good. And of course, we were interested: is that also possible to predict a kind of cholangiopathy with or without graft loss? And here's the area a little bit lower, but I think still quite good. 0.74 is the C statistic for fluorescence, and 0.76 for mass spectrometry. And what is, I think, important, we can also say something about kidney failure requiring renal replacement therapy. So there was a CETA statistic of 0.76 and with a fluorescence, and 7.1 with a mass spectrometry. And this is an important thing, because if we measure FMN release or complex 1 injury, as I said, this is not an on-off phenomenon. It is a kind of continuous scale of inflammation. It starts if you leave the green area. It starts that the patients need dialysis, and if you accept, for example, higher values, livers with higher values, you expect some biliary problem, and if you cross this line, there's a high probability for graft loss. And therefore, I think this is interesting and need, of course, further validation. But I think that would be interesting. And the argument which I frequently hear is how you know that the livers which you discard are really the right ones. So therefore, we put those livers usually on a normothermic device, which we also have, and we pump them normothermically. And you see what this is just an example: a liver which was discarded because of a crossing our threshold, clearly crossing the threshold with a very steep slope. And this liver was put on the normothermic device and had an AST and a level of 80,000, and also high ALT and necrosis everywhere after 48 hours. And therefore, I think it was correct, the decision. And so we try to prove ourselves and to make stainings for the docking side of FMN. If it is green, then the FMN is sitting in complex 1. If it is black, it is released. So everything in the discarded livers at the end of HOPE, which are black, so we don't take them, is the message here. And this is correlating with high FMN. So I think it is relatively clear that we make here hopefully the right decision. But all these ex situ perfusion machines cause kind of mitochondrial injury to a different degree, and this enables us to assess organ viability. Otherwise, we would be not able to measure something if there would be no injury. So the basic of all these parameters which are available, like AST release, bile quality, bile quantity, they in principle they base on the fact that we cause injury during machine perfusion. And this is recognized also by other groups. So this is a group from Austria, which you know, of course, Annemarie Weissenbacher. So they measure mitochondrial function in a different way with different imaging, but it plays an important role also from their point of view, and also others which try to measure by spectroscopy, also light, but they measure the cytochromes directly, but but the disadvantage is if you, for example, put a laser on the liver, you measure only one point. And the beauty of measuring perfusates is that you measure the accumulating release of everything which is released from the liver. So it's not only one point. So I think it is interesting for the community, because if we, for example, compare that with the available scores like DRI or DMED or other things, they all come too early, because they come obviously before, for example, the DCD process is introduced, and therefore they cannot be correct, because they don't include the warm ischemia or the hepatectomy time or the donor histology, and even not the organ transport. So therefore, I think it's makes much more sense to measure things during machine perfusion. The point is what to measure. That's a discussion, of course, probably also today. But machine perfusion has the advantage to measure after all the processes of warm ischemia, cold ischemia, and therefore is for me, makes more sense. For example, the comparison of the ROC curves for bar and DRI was disappointing. So we have only a statistic of 0.5 and 0.6 with the conventional scores of bar and DRI. So, and also multivariate, it played no role. If we look for the conventional parameters like donor age, donor BMI, cold storage, and even the graft risk defined by the UK score was not independent factor in the multivariate analysis of more than 1,000 HOPE-treated patients. We consider, therefore, this FMN story as a main advantage, and you see that we had a phase where there was increased cholangiopathy and also PNF. That was a time, because at the beginning of HOPE, we were thinking we can do everything with these livers except a 100-year-old or, I don't know, 90-year-old DCD with a warm ischemia time of 40 minutes and implant it, but this is not the whole story. So we saw complications, and we're thinking, okay, we need to recognize that, and therefore we introduced this graft assessment, and you see that we came down with the complications after introduction of this. The HOPE setup at the moment is very easy, because we put livers in a bowl. If we, for example, use VitaSmart and connect that to the circuit, and the vision would be that we have a sensor like here, which probably comes in the future, and we have the signal during perfusion here on the screen. That would be very nice. And then we have a liver graft quality check before use. Of course, we can add that with other methods. This is only the first step. We can measure other molecules like NADH. That's also feasible by spectroscopy or fluorometry. And we can measure the produced CO2 by special machines, which are very sensitive. We can just connect here the gas outlet of the oxygenator and see how the liver is breathing. Is also interesting. So there's a lot of things, I think, happening, and we can. But the point which I want to make is we can try to measure liver graft quality during HOPE, and that was very often questioned, because the liver is not doing much during hypothermic perfusion. At least in fact it's wrong. It's doing much, but you don't see it if you don't look carefully. My conclusion is there's a high number of liver offers currently. Still a high number is discarded. For example, in US 70% of DCD3 are discarded, so it's a very high number. And a more routine use of machine perfusion technology enables a more objective assessment of liver quality regardless of the method, I think, and therefore I think a significant number of liver grafts will be used with a further implementation of perfusion technology. Thank you very much. I'm happy to address your questions.